Yes, good morning, sir. Tapkire, sir.
Yeah, good morning, sir.
Yeah, yes, sir. Sir, please on your video. Yeah. Good morning, sir. Good morning. All the professors and the research scholar are here. Good morning, Tapkire, sir. Welcome to online 1 week faculty development program on electric vehicle, sponsored by AICT New Delhi, organized by Mechanical Engineering Department, VJTI Mumbai. I welcome to you, sir, in the session. Here all the professors from the various engineering college and the research scholar are here throughout the India. Uh,
Right.
yes, sir. Dear participants, dear professors and the research scholar, I just introduce about the Tapkire, sir. Mr. Abhishek Ashok Tapkire, working as a scientist in VRDE Ahmednagar, which is an esteemed organization of Defense Research and Development Organization, DRDO, Ministry of Defense, India. He does possess work experience of 15 years in the field of development of engine. Sorry. He is working on the development of vehicle type rotary engines for unmanned aerial vehicles and as a range extender in electric vehicle. He is a team leader in the indigenous development of rotary engine technology to achieve a nation's self-reliance in this critical technology. Sir has published more than 15 papers in various national and international conferences and journals. Sir possesses 7 patents applications on his name. Sir has been awarded by the prestigious Agni Award of DRDO for efforts towards the self-reliance. I welcome to you, sir, in the faculty development program of electric vehicle. I request you to share your knowledge and the experience with us. Thank you, sir.
Yeah, thank you, sir. Am I audible, sir?
Yes, sir. Uh, Dear professors, sir, audible to all of you? Hello?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yes.
Thank you. Thank you.
Yeah, good morning, all. First of all, I would like to convey my regards to Dr. Vijay for giving me this opportunity to interact with all the faculty in this faculty development program of VJTI. And uh, the topic of my presentation is a design of range extender, which is powered by the rotary engine, which is a vehicle engine that is for the electric vehicle. As we all know, the sustainable development is going to be a compulsion, and it is not going to be a want, but it is going to be a need. And the electric vehicle is the similar area where it has a long-term implications on the worldwide pressure growing on the environmental things. So that whatever we see about yesterday's budget, whatever we see about yesterday's budget also, that the government is introducing a scrapping policy 15 years and 20 years. Then recent victory of Joe Biden in USA and its commitment to the Paris climate meet, all it shows that the environmental targets and the regulations is going to be a compulsion, and it's not going to be a thing of luxury which is previously considered by the most of the developed nations. So that the next way, the complete decade, this decade will be dominated by the electric vehicle. As we saw, as we seen that there are various development in the area of electric vehicle, and the current the vehicle introduced as Tata Nexon, Hyundai Kona, then MG Hector electric vehicles in the Indian market, and the what we expect the entry of Tesla in Indian market, then we can see that next decade is going to be dominated by the electric vehicle. So that the topic of my presentation is about introducing a technology which will be very much helpful for any developing nation, just like India, where the charging infrastructure is quite limited, and we need to adopt this technology. However, there are some limitations in terms of infrastructure, and in terms of the pure electric vehicle, some of the limitations are there. What can be the other ways to introduce this technology in the Indian market, and which will have a important implication in terms of environmental targets. So I'm going to cover the concept of a range extender and the concept of rotary engine. Then the preliminary study, that is feasibility study, has been carried out for using the rotary engine as a range extender. Then what is the indigenous developmental efforts are there from the DRDO side for the UAV defense program, where this technology has already been developed. I would like to say that this technology of rotary engine, that is vehicle type rotary engine, is already been developed by the DRDO. There are two engines are there, 55 HP and 65 HP horsepower engines. These two engines are already been developed by DRDO, but that is for the UAV defense program, unmanned aerial vehicle defense program. That is for the aerial vehicle. But this similar technology, same technology, is having its important application in the area of electric vehicle as a range extender, which is considered as a series hybrid electric vehicle. Then what are design calculations are there for the tentative design calculations, preliminary design calculations has been carried out for utilizing this rotary engine, which is available for the automotive purpose, particularly for the hybrid electric vehicle. Then the case study of Tata Nexon has been considered, and the hybrid electric propulsion for the unmanned aerial vehicles. The electric propulsion is having an important role in terms of aerial vehicles also, because there are many experiments from the Siemens, Airbus for utilizing the hybrid electric propulsion for the aircraft side also, UAV purpose, UAV application also. So that has been feasibility studies been carried out. That introductory portion I'm going to present here. So I would like to confirm again whether I am audible, because I'm not getting any signal and other things, but I am audible to you, all of you.
Audible, sir. Yes, sir. You are audible.
Fine, sir. In case I am my link is cut off, Vijay sir, please give me a call on my mobile, because
Yes,
many
sir.
times, because my screen is not showing any signature that I am audible or not. So in case my link is cut, please give me a call on my mobile, sir.
Yes, sir. Yes, sir. I am there.
So why electric vehicle? As we all see, the electric vehicle is having the important advantage in terms of 3 E's. That is efficiency. First of all, efficiency. Then second is about economy, and third one, and the most important one, is about the environment. The environment is generally considered earlier on a lower side, but currently the environment is become a priority. That's why I told that electric vehicle will be the next, this complete decade will be dominated by the electric vehicles, because environmental regulations and pressures from the global side is going to be increased a lot. India has a commitment, India has given a commitment to the Paris climate meet. So we're abided to the carbon emissions. So electric vehicle is going to be very important, because the transportation sector will be have near about 1/3 contribution in the total greenhouse gases. That's why the scrapping policy, then the electric vehicle boosting, then the FAME 2 scheme, that is faster adoption of manufacturing of electric vehicles, FAME 2 scheme from the government. Then even from the state government side, then registration fees and all that things has been somewhat waived off. Then in most of the state governments are considering that proposals. And secondly, about even from the income tax point of view also, we can see that government is promoting the electric vehicles, the interest and all that things has been exempted. So government is boosting the electric vehicle, but why customer will opt a electric vehicle? If we consider a feasibility point of view, the first issue is about the range anxiety. There is an issue of range. The vehicles currently which were getting particular Tata Nexon, then MG Hector, Hyundai Kona, the electric versions are available. They are claiming there is a good mileage. If we see about Tata Nexon also 300 to 320 kilometers of electric range they are claiming, but many practical reviews are getting where we can see feasibly we're getting near about 200 to 250 kilometers of range in actual working environment. But many of the customers don't find it very lucrative. Then we have to drive the cautiously, particularly during the last 15-20% of the charge, the battery remaining portion state of charge is below the 20%. Then we have to drive cautiously. Then the speed is limited in terms of Tata Nexon. Also, the speed is limited to 120 kmph. So that the range anxiety is there from the customer point of view.
Sir, sorry to disturb. Hello.
Yes, sir.
Sir, are you presenting or?
Yeah, I'm presenting. My screen is visible to you?
No, sir. That's why I'm asking. Other participants. Hello.
Okay. My screen is not visible to you.
Not visible.
Yes, sir. Yes, sir.
Yeah, I'm presenting actually. Just 1 minute. I will just check it. Yeah, now the screen is visible. Presentation is visible.
Yes, sir. Yes.
Sir, please make it large.
Okay, now it is a full screen.
Yeah. It's good now.
Yeah, okay. This symbol is I am not getting. That's what I was confirming. Okay.
Okay, sir.
So I will go to first slide again. These are the areas we are covering about development of rotary engine as a range extender in electric vehicle, and this is about the introduction portion which I already covered. That range anxiety, that is why customer will opt for electric vehicle. The first one is about the range anxiety is there, and in case there is unplanned travel is there, then in that case customer is having somewhat apprehension about the electric vehicle. And the second, the most important thing is about the charging infrastructure. The charging infrastructure currently in most of the developing nations is absent. Even in case of India, this bidding and all that things are going on, but the charging infrastructure is somewhat on limited side. Even the government is pursuing very hard, but charging infrastructure currently is absent, and there is a higher charging time also. And if you see about increasing the range of the vehicle, just like Tesla, they are going to near about 500-600 kilometers practically, or even more than that. Then in that case the initial cost of the vehicle is going to be somewhat high. The reason behind is the battery cost is going to be very important, because in the electric vehicle near about 1/3 cost will be the battery cost. And so that if you are going for a higher range, then in that case the cost of the vehicle is going to be increased. Even in case of a Tata Nexon, the petrol and diesel version is available near about 8 to 10 lakh, while the electric version is about going to near about 15 lakh. Even though we're having a limited range in this area, but if we are going to increase the range, then in that case battery cost is going to be very significant. That is going to be an issue. So there are two issues are there. One is about charging infrastructure, and second is about the range. How to adopt this, how to make this, how to remove this two lacunas in the electric vehicle, so that it will be coming in the range of economically affordable segment, just like we can say near about 7 to 8 lakhs or near about 10 lakhs, where electric vehicle will have a dominant advantage compared to the IC engine vehicle. So this technology of the range extender is there. Range extender is nothing but a range extended vehicle is nothing but an electric vehicle which will have an onboard generator, where in the vehicle itself, in the boot space, there will be a small engine will be there. It will be a small engine, and it will be fitted in a boot space which will run at constant RPM, and it will be operated only when the state of charge of the battery will be somewhat below the certain lower value, just like 20% or 15%. The reason behind it that majority of the portion, the vehicle will run on a electric mode. But after that, the range extender will be started, and this range extender, the purpose of the range extender is only to charge the battery, and it is not going to run the electric motors. So that this will be the role of a range extender. So that what we can say, near about greater than 85% of the time, vehicle will be running on a electric mode only, and once in a while, when there is a need to go beyond electric range, there will be a utility of the engine. So that if you see about this schematic, the right side schematic is there. This is a small capacity. This is an internal combustion engine, which is a small capacity internal combustion engine, which will be connected to the generator or alternator, and there is a separate battery will be there. So power converter, the connections will go to the battery, and through the power converter, we're running the through this primary motor. We're going to give a drive to the vehicle. It is going to be a series hybrid electric configuration, but it is not a series hybrid vehicle. The difference between this is, in series hybrid vehicle, there is no provision of the external charging. Here the plug-in charging will be there. Secondly, in series hybrid electric vehicle, engine will be continuously on. Here in this case, engine will be on only when it is needed and when we want to increase the range of the vehicle. So that we can say that the fuel combination, battery combination, and the external plug-in combination, both all three combinations will be available for the range extender configuration. As I already told that it is a series configuration, then the thing is that in this case we can limit the electric range of the vehicle. So suppose currently near about 200 to 250 kilometers of electric range we are getting. Then in that case, but most of the customers will utilize this range, particularly in terms of personal cars. Once or twice in a month, we can say that the more than 150 kilometers of range will be utilized in a day. So what can be the alternative? That near about 125 to 150 kilometers of electric range can be given to the vehicle, and in case the vehicle range to be increased, suppose near about 300, 400 or 500 kilometers, in case some long journey is there, in that case, after 150 kilometers, this engine will be started, and engine will charge the battery, and it will supply it to the electric motor. That will be electric drive. So that most of the 85 to 90% of the time, we are going to utilize the electric portion of the vehicle during the entire life course, we can say, and near about 10 to 15% of the time, this range extender plus electric combinations will be used. The reason behind this is that there will be less dependency, particularly on the charging infrastructure, because we are having the engine with us, and the customer's apprehension about the range that can be eliminated. And secondly, the cost of the vehicle can be come down. I would like to say that Mahindra and Tata both are also working on range extended electric vehicles to make this electric vehicle particularly in an economically affordable segment. So that here the advantage we are getting is that the first of all, this engine will be a lower capacity engine. Why it will be a lower capacity engine? That I'm going to explain it in the next slide. But suppose there is 100 horsepower, so 100 horsepower of vehicle is there. The engine capacity here required will be near about 30 HP only. So there will be a low capacity engine will be there, and second, so that, and again this engine, IC engine, that will be run at constant RPM and minimum BSFC position, so that it is at its most efficient zone. There will not be any fluctuation in the engine RPM. So we're getting the engine operating region, which is the most efficient region, where we're getting a minimum BSFC, so that we're getting the advantage in terms of engine portion. And secondly, in terms of motor control, in terms of electric portion, we can say that the torque speed characteristics of the electric motor and the tractive effort and vehicle speed, the characteristics, both are nearly matching. So that there is no need of any gearbox and other things are there, so that the characteristics are going to be matched. That we're getting the advantage in terms of electric traction also, so that electric traction will be at its efficient zone, and engine is also at its efficient zone, so that we're getting the advantage. Both power source will be at in efficient operation. Then there will be a reduced need of maintenance. Electric itself is having a lesser maintenance. and engine will be have a lesser maintenance because the life of the engine will utilize will be very less. The longer life cycle will be available. It will have a good ecological advantages, either in terms of disposal of batteries because battery capacity itself is lesser is required. Secondly, the engine will be operated only for the 10 to 15% of the time, considering the customer characteristics in terms of personal vehicle, so that we're getting the advantage both in terms of engine and electric vehicle side. Now I will go to the next concept. Here we can say that the full hybrid, if you see about the G column, this is a full hybrid thing is there, which was earlier available, and now we're jumping directly to the electric vehicle. That is going to be very fine, but we're having the disadvantage in terms of initial cost, so that we can till the charging infrastructure is there, and still till the some good technological breakthrough in the battery technology, the range extender is going to be a somewhat feasible option, where the customer perspective can be considered, where it will be available in the economical range also, and we're getting the advantage in terms of electric plus ICE engine advantages, both we are utilizing in this range. So instead of directly going to the electric vehicle, the in between range of range extender ICE engine is available, where the plug-in option will be there and engine plus electric motor option will be there. Now we have seen the advantages of the range extender. What will be the limitations? We can say that it will be a lesser efficient mode because we are converting power twice, but it will not be a very much lesser efficient, just like 35%, 30 to 35% in terms of ICE engine. The power plant propelling the vehicle, the sizing of the power plant will be decided by the vehicle. Then increase running cost to some extent because total in terms of in 85 to 85% of the time the electric mode will be there, so that we are getting the advantage of electric mileage. But when engine and electric both will be operating, in that case, at about 15% of the vehicle the running cost will be somewhat on the higher side. Then it is adding somewhat design complexity to the powertrain, even though it is going to be somewhat simple because we're adopting a series hybrid electric configuration. The maintenance and reliability aspects will be on somewhat on higher side because we're adding an engine, and the refueling has to be done at the petrol stations and recharging at the home or public charging. That both recharging we need to do. But whatever the limitations are there in terms of range extender side, the advantages are much more important, and much advantages outweigh the disadvantages. If we see about the customer perspective, I already explained that generally the pursued maximum trip distance is going to be an important criteria. Suppose one person is staying near about 150 to if you consider the example of your Mumbai also, near about Pune, if you're considering the example, then near about distance is about 120 to 150 kilometers. If to and fro distance is there, if 300 kilometers is going to be consumed within a day, this condition is going to come once in 2 or 3 months, but it is affecting the his purchase decision based on this pursued maximum trip distance, because charging infrastructure in between is not available. Secondly, from the ecological point of view also, ecological perspective also, that how to from the customer perspective point of view, that if a range extender is there, then in that case there will be a boost to the electric vehicles, electric plus this range extended vehicle, because in case he just want to increase the range of the vehicle to near about 400 or 500 kilometers is going to be possible. And from the ecological perspective also is going to be important. Then one more important thing is about the range extender has to be gasoline only, and there is a more boost to the gasoline thing currently, considering the emission point of view. The reason behind using the gasoline engine is the pollution limitation of the diesel vehicle. Then there will be a lesser cost of the petrol engine first of all. Then lesser noise and vibration is there, lesser maintenance cost is there, and the most important is that these alternators, particularly in the currently going scenario, the alternators, high speed alternators are available, and for the petrol engine is having somewhat on a higher RPM. So that high speed alternators and which is going to be somewhat efficient alternators, So that high RPM of the engine, higher RPM of the engine, that is going to be a good match. So that gasoline engine is going to be important as a range extender. Then what are the other options are available is about the fuel cell. For fuel cell is having the important advantage in terms of zero emission. It's the hydrogen is having calorific value near about 3 times the petrol and diesel, near about 1.2 lakh kilojoule per kg, and the low weight, unlike a battery vehicle, but it's having the limitations currently in terms of technology is about its safety. It's about storage and availability of the rare earth materials. Reciprocating engine is also having an important option as a range extender because of its high proven its trust, and it's 120 years of established technology. And this is about the trailer configuration. If you see on the right side, such type of things are currently been tried in Europe, where the electric vehicle, this will be a pure electric vehicle, and in case this electric vehicle, in case the customer has to go to the higher range, particularly near about 400 or 500 kilometers, which is beyond the electric vehicle, then such type of trailer configurations they are currently adopting, but which is not going to be very much feasible in Indian scenario. Sir, my voice and all that things is all right, sir? Vijay, sir?
Yes, sir. Yes, sir.
Fine. Now, the next concept is about the Wankel engine.
Please switch
Next
off the
concept is
video. Anyone participant is there? Jaipal Patil, sir. Thank you.
yeah, this animation is visible, right, sir? Okay, this is the configuration of the Wankel type rotary engine. Here you can see here you can see that this is a typical reciprocating 4-stroke engine, and this is a Wankel type rotary engine. The Wankel type rotary engine, this is a configuration where there is a triangular shaped rotor is there, and there is a epitrochoidal shaped housing. This is a epitrochoid, and there is an internal epicyclic gear train is there. And this internal epicyclic gear train is giving, it's having the 2:3 ratio, and it is giving 1:3 output. That is when there is a 1 revolution of the rotor, there are 3 revolutions of the output shaft. This is the area where there is a suction is there. Then there will be a compression. Then spark plug will be there, which will fire at near about 18 degree before top dead center. Then there will be expansion stroke, and there is a exhaust stroke. Here you can see that the complete things is rotating. There is no conversion of reciprocating motion into the rotary motion. Here directly the rotary motion is converted into the rotary motion. So that's having the advantage in terms of balancing also, and it's having the advantage in terms of its compactness also, because the configuration itself is very compact. Secondly, if there is a 1 revolution of the rotor, there are 3 revolutions of the output shaft. You can say that 3 revolutions of the output shaft is 360 multiplied by 3. It will be near about, it will be 1080, and in this 1080 degree, there are 4 strokes are taking place. So that 1080 divided by 4, it will be 270 degree. So that each stroke in the rotary engine is about 270 degree, which is the case in case of a 4-stroke engine, it is 180 degree. So that each stroke in the Wankel engine is 1.5 times larger compared to the 4-stroke engine. So that we're getting the advantage in terms of volumetric efficiency. Apart from that, we're getting the advantage in terms of torque fluctuations. So these are the important advantages of Wankel engine. Then there is a low, because of this mechanism itself, we're getting a high power to weight ratio. It's having the low frontal area, so that its specific weight is going to be very high, specific volume is going to be very high. Then it's having the lesser vibration and noise, because we're converting directly rotary into the rotary motion. It's having the high volumetric efficiency, because I already explained that near each the suction stroke is 1.5 times larger, so that we're getting a more time for induction of a charge. There will be a smooth operation, and there will be less complications. There is no wall train is required as a port mechanism currently we are using, and which is quite efficient also in case of a Wankel engine. Then the number of internal rotating parts are quite less compared to the reciprocating engine, so that the power loss due to the internal friction will be less. Then it is a gasoline engine, and it will be a silent operation is there. Then so for the long idle time operation, it is going to be very much useful. And I would like to say this technology is indigenously available with TRDO. The VRD has developed this technology for the unmanned aerial vehicle application. There are 2 unmanned aerial vehicles are there of our Indian defense, that is UAV Nishant and UAV Panchi. For this UAV purpose, this technology has already been developed, and it has been delivered also for the utility. And I would like to say this is the first airworthiness certified engine of the nation in non-gas turbine category. And in gas turbine category, there are engines are available, but in non-gas turbine category, this is the first airworthiness certified engine by the Center for Military Airworthiness Certification. There is a regulatory body for the Indian defense aero application, that is CEMILAC, and this engine is certified by them. Yeah, this is the sealing mechanism of the engine. Here the important seal is apex seal. The seal will be directly in contact with the surface, and below that there will be a spring will be there, and this spring will push the seal towards the surface, and there will be a separation of the chambers will be there, so that in different chamber different strokes are taking place simultaneously. And there here when there is a suction, here the simultaneously expansion is going on, and here the combustion is going on, so that simultaneously different strokes are taking place in the different chambers. The currently technology developed by the VRD, it's having the capacity of 55 HP and 65 HP. It is running at the higher RPM, that is 8000 RPM. It's a one carburetor version and electronic fuel injection version is available with us. And its cooling, if you see, its cooling is liquid plus air cooling. Both are available. The housings are liquid cooled and internal portion is air cooled. And if you see about the weight, particularly the weight, I told about the power to weight ratio. Its weight, if you see, near about 55 HP engine is having 28 kg of weight, dry weight, and 65 HP engine is having 32 kg of weight. In about 0.5 kilogram per horsepower we are getting, which is quite important advantage as a range extender electric vehicle, because we require higher specific weight, because its weight has to be low and its volume also has to be low. We should get a higher horsepower also. So that's compression ratio. The compression ratio is 9.2, 9.5. It's the gasoline engines. The total loss step lubrication system and sealing ignition system we have used in this engine. So this is about the presentation. Yeah, this video is there. Now I think I would like to show the video at later stage, because it's in the presentation mode and I think it's not running. No issue. The development of the vehicle engine, I would like to say that I would try to run the video at the end. The engines currently we have developed also, and we have given it to the UAV application. There are flight trials, high altitude trials, and other trials also we have done. And it's a proven technology in terms of UAV, and same technology can have an important utility in the range extender. So now the feasibility study was carried out. Sir, what's the time available to me? It's about 1:15, right, sir?
Yes, sir. 1:15.
Okay. Then the application of existing rotary engine as a range extender for automotive purpose. Then currently the engine which is available with us, that is 65 horsepower. And if you want to utilize this engine, then which application currently, which range of vehicle will be suitable for it as a range extender, that I'm going to explain here. The first one is about the specification of the what will be the design methodology for that if the existing engine is available, and if you want to utilize it for the purpose of automotive application, electric automotive application as a range extender, then what will be the methodology that I'm going to explain. First one is about the specification of the engine. It's clear to us that is 55 and 65 horsepower engines are available. So first of all, we have to estimate the actual power available at the alternator end. When the engine is available with us, we are connecting the alternator to the engine, and what will be the power available at the alternator end, that we need to consider. The three important things are there. First one is about the altitude derating. That is, with respect to altitude, there will be some derating will be there. Then we can't run the engine at max power, as we have to run the engine at minimum BSFC position, and there will be alternator efficiencies there. Then what will be the power flow line degradation will be there. That is the efficiencies in terms of motor, charging, discharging, and transmission. Then what will be the power flow degradation that we need to predict. Secondly, the driving cycle we need to determine for the electric vehicle. For that is that is we have to determine the ratio between peak power and the average power. Then we have to select the mode of the range extender. That is whether the range extender required is a charge sustaining mode or charge depleting mode or charge improving mode. What is this modes are there? I am going to explain later. Then we have to estimate the motor power range. Then what will be the electric range, pure electric range which will be needed, that we need to decide. It may be based on the regulation or as per the standard. If we see about the most of the European regulations, then in that case they have defined that near about at least 120 kilometers will be the, in terms of miles they are referring, but in terms of kilometers, 120 kilometers of electric ranges is compulsory in case of a REX, that is range extended vehicles. And the range extender should not start before the state of charge is before the state of charge, if the state of charge is greater than 6.5%. Such type of regulations are there in European nations, but currently in India such regulations are not there. Then we have to select the control strategy, that is whether what will be the state of charge we need to put in terms of starting the range extender, and based on that control strategy to be determined. And we have to generate the battery power specification, what will be the battery pack required for the minimum electric range, and as per the vehicle capacity that we need to determine. If range, weight, space and cost, if all the things are within limit, then we can go ahead with the range extender finalization. Otherwise, the mode of the range extender to be changed and these things to be iterated. The first one is about calculating that engine rated power is there. Whatever the 55 and 65 horsepower I told, that is the engine rated power. And what will be the power available at the alternator end, that we need to determine. The first important point is about low BSFC RPM. That is, we need to run the engine at a lower BSFC. If we see about this is a curve of brake SFC, that is BSFC, and brake specific fuel consumption is coming in near about 70% of the max RPM, approximately 65 to 70% of the RPM. So that this will be the low BSFC point we need to follow, where we are getting a maximum power and minimum fuel consumption. And secondly, if we see about this curve, this is a brake power curve, and brake power curve we're getting a continuously increasing. In case of a vehicle engine, we're getting a continuously increasing power. This is a representative purpose. I just put it from the book point of view. This is not actual data of the vehicle engine, but as a representation purpose, I am showing this. That brake power is continuously increasing, and after a certain time it is going to be decreased. But near about maximum RPM, we're getting a maximum power, but minimum BSFC RPM will be about near about 65 to 70% of the maximum RPM. So that we need to run the engine at 70% of the power, so that there will be a degradation in engine power, because we need to go for a higher efficient engine. And secondly, over here in the minimum BSFC portion, we are getting the maximum combustion efficiency. Here we are getting the high volumetric efficiency, and friction is also going to be on a lower side. That we are getting important advantage from the engine at minimum BSFC RPM. But here we need to compromise. There will be a penalty. We need to compromise on the power side, and there will be a penalty on the power side, because we can't extract the maximum power from the engine. So that power reduction from the rated power we can consider near about 22% here in this area. The second thing is about the altitude correction. Whatever the engine's power is mentioned, 55 HP or 65 HP, even in terms of automotive also, this is having the corrected powers are there. So that these corrected powers, they are corrected for the standard temperatures and pressures. So that practically, if you are going for a different altitude, just such like Manali or somewhere else, or in terms of Leh, or if you are running the vehicle at the Mumbai and if you are running the vehicle at the Manali, there will be a difference in the engine power. And that while designing the thing, we need to consider on a pessimistic side, so that altitude correction also we need to consider. The rated power is the corrected power, and it is to be corrected for the altitude power loss. Here, as from the design point of view or from the calculation point of view, I consider near about 6,500 feet. Why I consider is the 6,500? It is somewhat on the pessimistic side itself. Near about when I considered the altitude of Manali, where it is 6,500 feet is there. Although the Leh and Changla near about 12,000 feet and 15,000 feet, 17,000 feet data is also available with us, so that whatever the actual power available at the critical altitudes, as altitude, that also we're having the data. So if I consider near about 6,500 feet, near about 2.5% or 3% per 1,000 feet is the normal degradation we can see in terms of power. near about 20% reduction in the power we can see. So that one is the lower BSFC RPM, second is about the altitude correction, and the third important thing is about alternator efficiency. Alternator efficiency here I consider is about 90%. So the whatever the 55 and 65 horsepower engine which is available with us from the alternator end, what power will be available to us is about 23 kilowatt and 27 kilowatt. So that the alternator which we need to use should have a capacity of 23 and 27 from this 55 and 65 horsepower engine. So that the power available at the alternator end we have calculated. Yeah, here in this graph I would like to say that this is the engine power versus speed, and this is the BSFC lines are there, and here we are getting the minimum BSFC. If you see about 255, this 255 grams per kilowatt hour, and this 255 zone we need to see, and we can see that this is the maximum power portion, and we need to run the engine at a minimum BSFC so that we are getting a lesser power compared to this. Near about 20-22% reduction will be there. Here I already mentioned that by compromising at for compromising for running the engine at low BSFC RPM, nearly there will be a reduction of 22%. And this is data of Lycoming that there will be a power degradation with respect to altitude, and near about 2.5 to 3% will be the power degradation. So that we have calculated that the rated power at the alternator end. Secondly, about the rated power at altitude correction, minimum BSFC power we considered. The thermal efficiency of the engine is 30%. The power available we can say we are getting here. Then there will be a battery pack will be there. The alternative is supplied to the battery pack. There will be a charging and discharging efficiency will be there. Again, there will be a separately plug-in hybrid plug-in option will also be available. When the vehicle charging will be there, it's about near about 92% we can see. And motor efficiency also we need to consider. Motor efficiency is about 90% we have seen. That near about 90% has been considered. So that this is a complete power flow line that we need to consider, and the losses in the power flow line has been considered here. Secondly, I already told that when there is a 100 HP of engine is there in some automotive IC engine, conventional IC engine vehicle, the range extender capacity is going to be very low. The reason behind is explained in this slide. The first one is about if we see about the load power, this is the load power. And with respect to time, the vehicle will run with the load power. This is going to be a characteristics. But the thing is that there are two components of that load power is there. One is about the average power, and second is about the dynamic element or transient element is there. That is the dynamic power. This average power and dynamic power we consider the load power. These two element, out of this two element, the average power will be supplied by the range extender. However, this dynamic power will be supplied by the battery. So that there is an important advantage that we're having a battery, and this battery is an important energy reservoir. When there is a transient response is there, when there is a higher power requirement will be there, that will be catered from the battery side, and the average power requirement will be fulfilled from the range extender. So that in terms of load power, whatever we have seen that in about 100 or 120 k, 130 k, 130 HP engine which is available in the our vehicles, they are considered they are designed for this the peak power in the load power range. Because of this peak power, we have to go for a bigger engine. However, the range extender has to supply the average power, so that low capacity engine will be there, and for a temporary or transient period of time, transiently we are requiring a higher power, then that will be from the battery. So that if you see about the driving cycle, this is just representation. This is going to be a driving cycle, and the average power, if you calculate, this average power will be supplied by the range extender. However, in the conventional engine, this is the range. This is the power requirement that has to be catered by the engine, so that the engine capacity is somewhat on higher. However, the range extender capacity will be on the lower side. Now, what is affecting it? I consider in this case, when the initial feasibility study, that ICDC, then the Indian driving cycles I consider, city driving, highway driving, and express highway driving cycle, and average power to the peak power ratio has been calculated, which is coming in between 19% to the 33%. So that in most of the cases, near about 20, there will be a requirement of the range extender in the highway range and express highway range, because where we exceed the electric range and the vehicle has to run for a longer period of time. So that this is going to be an important range, that is 22% to 33% range will be important, so that the average power to the peak power will be about 22 to 33%. So that the range extender capacity will be about we can say 22 to 33% of the maximum power requirement in terms of a vehicle. So we can say that if engine power, that is range extender power, if I am keeping greater than the average power, then it will be a charge improving mode, because engine is going to supply more amount of charge, more amount of power than the vehicle requirement, that is average power, so that the battery charging will be on a higher side, so that it will increase the charge of a battery, so that it is a charge improving mode I'm considering, because SOCs, that is state of charge of the battery, will increase. If engine power and average power is going to be same, then it will be a charge sustaining mode, because if suppose at 20% state of charge of the battery, if range extender is started, then averagely if you see the 20% charge of the battery will be maintained if engine power and the average power will be similar. Then if engine power is lesser than the average power, then it will be a charge depleting mode. If 20% of the state of charge of the battery is going to take the vehicle, suppose for the 50 kilometers, if engine is going to be started, which is having the lesser capacity than this, then instead of 50 kilometers, vehicle can go to near about 250 or 300 kilometers, because engine power is less compared to the average power, and it will be a charge depleting mode. Here the charge of the battery will be depleted, however at a very slower rate. So these are the three different modes of battery state of charge. Yeah, now this is a theoretical estimation. This is theoretical estimation. We can see that near about 22 to 33% will be the range extender power. Now I have made a practical study also in terms of some of the experiments done in the area of series hybrid electric thing, plug-in hybrid electric vehicles, and range extended electric prototypes also developed by the Mazda and Mahle. Some of their data has also I have analyzed, and based on this data, you can see that based on this data, the last range you can see that the engine alternator power to the motor power, that is peak power of the motor, and the engine alternator power, it's having the ratio of near about 40% to the 30%, 20% to the 40% range. However, Chevrolet Volt is a different vehicle. But practically, we can see near about 20% to the 40% will be the range of the is the range where that is the ratio of alternator power to the motor power, so that the alternator power or the range extender power at the alternator end requires near about 20% to the 40% of the maximum or peak power required from the motor side. It's going to be hanged, I think. There is a lag, sir.
You can stop the presentation and then again you can do that.
Yeah. Yeah. This is the next slide. Here again, some calculations I have shown that a 55 HP horsepower engine is there. Rated power in terms of kilowatt is calculated. Altitude derating we need to consider. Minimum BSFC we need to consider. Alternator efficiency we need to consider. Then the charging and discharging efficiency from the battery, we need to consider motor efficiency and what are the power available at the alternator end, that has to be calculated. And if this power available at the alternator end is about 23 kilowatt and 27 kilowatt for the both the configuration, then it will be suitable for near about 125 125 horsepower of vehicle in a charge depleting mode. This 55 horsepower engine will be suitable in charge depleting mode and charge sustaining mode for this power range of vehicle. And if you go for a 65 horsepower, it will be it will be suitable to 120 to 145 in different modes of in charge sustaining range and charge depleting range. So that this is the range. If you see about
Sir,
120.
please, can you make it full screen? Full screen?
Yeah, is it now okay?
Yes, sir.
Yeah, it is. It will be suitable in charge depleting range and charge sustaining range for the different capacity of the vehicle. So that fairly we can see near about 120 to 130 120 horsepower of engine in charge depleting range. 55 horsepower is suitable, while 65 horsepower engine will be suitable in charge sustaining range for the near for this range of 120. And this is a similar range of Tata Nexon, and this is a similar range of Tata Nexon, we can say. And for the Tata Nexon, so I consider the example of Tata Nexon here after this, and I just want to make sure that from the first principle point of view, whether these calculations are correct or not. So that this is the conclusion from the initial primary calculation that for 25 to 30% range, near about 25 to 30% range will be the 25% range will be the charge depleting range, and the 30% will be the charge sustaining range. And this is the power capacity where it will be somewhat suitable. This 120 to 125 horsepower capacity is the capacity of which is closer to the Tata Nexon. So now my next calculation I had done for the Tata Nexon. The why I took an example of Tata Nexon, the first of all, it is a indigenous vehicle. That is a thing of pride for us, and it is a vehicle which has dominated the electric vehicle market. And the attempt by the Tata in terms of electric vehicle in Tata Nexon is a really important milestone in this complete electric vehicle journey. First of all, it is an indigenous product, and secondly, the electric vehicle and the conventional fuel, that is the petrol and diesel vehicle, both are available in Tata Nexon, so that it's easy for me from the technical point of view to compare the data with the conventional electric vehicle. But the initial, whatever the initial calculations were done is about 25 to 40%, which is a wide range, because 25 to 40% itself is a wide range, and this ratio will be changed. There will be a ratio variation will be there as per the different parameter, just like vehicle variables are there. Then in terms of vehicle variables, this ratio will be changed if a vehicle mass is on a higher side, if vehicle is on a lighter side, its capacity, then the other weights in the complete weight of the vehicle, then loading capacity and other things are there. This ratio will be changed. Second is about the driving cycle. If we are going for a European driving cycle or Indian driving cycle, or for US federal driving cycle, then in that case there will be a change in the variation. There will be a variation in this range. Then third one is about the control strategy. The control strategy, on-off control strategy we are adopting, or thermostat control strategy, or on-off control strategy, or degradation control control strategy. What strategy we are adopting, that control strategy is also going to decide this range. And in case we are using some energy conservation technique, just like in case of most of the electric vehicle, that regenerative option is available, that energy conservation and all that things will be available, that energy conservation techniques are there. Then because of that energy conservation techniques, there will be a power flow line and other calculations will be there, which is also affecting this range. So that I took example of Tata Nexon, and I had to try to correlate and try to take this all the parameters and try to find out whether what will be the calculations from the say from the first principle. So that we're having some vehicle, suppose this is the Tata Nexon electric vehicle is available with us, and if you want to design a range extender for that, so what will be the strategy for that? Now from the first principle point of view, we'll go that the specification of the vehicle has to be determined, then characteristics of the route or driving cycle we need to determine. So what is the driving cycle we are considering, and that is going to be very important, because the ratio of peak power to the average power depends on the driving cycle. Then just like in terms of engine, we're doing that. Whatever the tractive efforts will be there on the vehicle, the tractive efforts we need to determine. Then we have to determine the estimate the average power based on the driving cycle. Then what are the consideration? The losses will be there from the engine from the alternator end towards the wheel, where we are getting directly the torque. We are giving the torque to the vehicle. In the complete power flow and whatever the losses will be there, that we need to consider. That the engine losses, efficiency of the alternator, motor, charging, discharging, and transmission also we need to consider. Then mode of the range extender we need to determine. Then electric range as per the regulatory standard that we need to see. Then control strategy to be adopted, and we need to generate the specification of the range extender and battery pack both based on this data. That battery pack and range extender specification has to be determined. Battery pack will be determined based on the pure electric range. Range extender capacity will be determined based on this all complete calculations. If all the parameters that's like range, weight, space, and cost is within limit, then we can freeze the dimensions, and otherwise we need to go for a changing mode and we need to see the calculations. Yeah. Now in this case, I considered on-off control strategy. That is on-off control strategy has been used where when the charge is at higher line, suppose 30 to 80% we are considered, 80% the state of charge of the battery. For the charging point of view, if you consider, suppose at 80%, engine will be in off condition. If battery is degraded from 80% to the 30%, then in that case engine will be started and the vehicle will run continuously. There will be a power loss from there will be a power requirement from the vehicle will be fulfilled. Apart from that, if engine is having the higher capacity, then there will be a charging of the vehicle, and it will charge the up to the 80% again, and then again engine will be off, and again there will be a discharging cycle. So that is on-off control strategy has been considered, which is also known as thermostat control strategy. Just like based on the principle of thermostat, that is on-off principle. Yeah. Now the vehicle dynamic model has been considered here to calculate the various tractive efforts. First one is about the aerodynamic resistance. Then second is about the rolling resistance and grading resistance to be calculated. And the most importantly about the acceleration resistance to be calculated. This all resistance to be calculated. Then the summation will be the force on the vehicle. Then power of the vehicle will be the force on the vehicle multiplied by V. Here the important is aerodynamic resistance is going to be important at higher speeds, because here the V square ratio is there, and apart from that there will be a velocity of the vehicle, so that it is going to be a cubic curve, so that aerodynamic resistance is going to be very important. Then if the power of the vehicle is calculated, the range extender vehicle capacity to be calculated. Range extender capacity will be power of the vehicle, and if you deduct the efficiency of the transmission, motor, and charging discharging efficiency, then we can get a power of the range extender. So the power of the vehicle divided by if a transmission, motor, and charging discharging efficiency, we can get the power of the range extender. Here to calculate this average power, the first important thing is about the calculating the average power. There are two strategies are adopted. First is about the directly from the cycle we can calculate the average power. So that for that thing MATLAB simulating model to be generated, and from the MATLAB simulating model by giving the various inputs and by putting this all the parameters directly from the cycle, we can calculate the exact average power for the vehicle. And second strategy is about the simple strategy is about the average power should be greater than the power for max constant highway speed of the vehicle. Suppose in case of a average suppose in case of a max constant highway speed, if you consider is 100 kmph in case of a expressway or normal highway driving, if the vehicle is going at near about 100 kmph, then what will be the average power of the vehicle? That can be considered as the average power of the vehicle, not the max power, but the average power of the vehicle that can be considered. Such type of strategy is also there. If we're going for a cycle, then in that case, all the parameters with respect to time domain we need to calculate, and by considering all this data, we can calculate for a average power. Now, in this case, I consider the near about 100 kmph of constant speed for the Tata Nexon, and this is going to be, I consider this is going to be average power of the vehicle, not the max power, but the average power. What are the parameters I considered here for the calculation purpose is the curb weight, engine alternator, and liquids, other parameters, other weights also been considered. Battery weight will be somewhat on lower side. That also been considered. Then occupants weight, 4 occupants are considered, and the weight is calculated. Then the rolling coefficient resistance, aerodynamic coefficient resistance, and frontal area from the calculations are considered. And near about and the motor drive is 96 kilowatt motor drive is there in the Tata Nexon. So these are the specifications of the first step of specification of the Tata Nexon has been determined. We're having the limited time. I need to cover it somewhat fast. I think it's hang again. Yeah, this is a different calculation. Here we can see that load power versus vehicle speed, we're getting a cubical curve, and at 100 kmph the load power has been calculated. 100 kmph near about 21 kilowatt of power is coming, and for range extender power, the average power has to be divided by means of transmission motor and charging discharging efficiency. It's coming about 27 kilowatt, and which is if you consider about the motor power to the extender, the range extender power, it's about 28.34%. So whatever the initial estimate is there, based on the initial estimate of 25 to 40%, we can say that near about 25, the initial estimation of 25 to 40%, we can say on the basic principle, from the first principle also near about 28% will be the average power, and the range extender power is near about 28% in case of a Tata Nexon. In that case, we are getting a charge sustaining range. So near about 25% will be the charge depleting range, and the 30% we can see consider as near about charge sustaining range. If we're going for 35%, then it will be charge improving mode. It's not only about the 100 kmph. If the vehicle is going at near about 42 kmph, near about 5-degree gradient also can be achieved. Just like for the same tractive efforts, if you see that instead of 100 kmph and instead of 100 kmph, we are running the vehicle at near about 40-45 kmph. So the 5-degree gradient also been achieved with the same range extender power. Yeah, this is a summary of the results. It is the same thing which I explained. Second is this application is also having the importance in terms of auxiliary power unit, which is required for the defense application. There is a huge demand, and for the same engine, if we want to go for a auxiliary power unit for any defense application, then the calculation will be on the similar side. That engine we need to consider the corrections are there from in terms of minimum BSFC altitude, and in terms of alternator losses that we need to consider. We can develop an auxiliary power unit for the defense application. And I would like to quote that the engine is having the important advantage in terms of weight and in terms of volume. So from the defense point of view, when there is a constraint of weight also, and there is a constraint of volume also, so that this application is going to be very important from the APU point of view. This is a comparison with the Honda generators, which is commercially available. Actually, it is not very correct thing to compare it with the commercial generators. But similarly, near about within 200 kg, we can get near about 27 kilowatt of APU with other units, while the commercial alternative will require near about 500 to 600 kg of weight. And second, the other important application, although it is not from the electric automotive vehicle point of view, but it's from the electric unmanned aerial vehicle point of view, that I would like to explain within 5 or 10 minutes. That if we are to use this concept of range extender of electric vehicle, or this vehicle engine concept, which is a hybrid electric propulsion, which is a series hybrid electric propulsion, but we have to use it for the aircraft UAV application, unmanned aerial vehicle application. What should be the approach for it? That I'm going to explain now. And for this thing, the hybrid electric propulsion for the UAV, that is going to be very much important, because whatever the advantages we are getting in terms of automotive application for the electric vehicle development, that the say in terms of battery, in terms of electric motors, in terms of the alternator, in terms of generators, whatever the developments are going on, so that this field of aerodynamic field is also going to be very much affected. And there are experiments from the Siemens, even from the Airbus, Siemens, and many other European players and US players for development of a hybrid electric propulsion. And For that thing, we need to see whether the same concept can be used for the UAV purpose. It's having the important advantage in terms of high reliability and power source and propeller. The propeller and power source currently has to be at a single place. Here, multiple places we can give, and we can increase the aerodynamic efficiency. And it is again a safety mechanism will be available, because the reliability of the motors will be very high compared to the other parts. But there will be important challenges, because automotive and aero is having the important challenges in terms of energy density. So hybrid will utilize both in terms of so here in this concept, I consider engine plus battery plus solar power, all the consideration I considered. The aircraft weight is calculated. Then based on the fuel capacity, I am considering the example of Rustam 2 UAV. I would like to say the Rustam 2 is medium altitude long endurance aircraft, which is developed by the Indian Defense, and currently it's having the weight of it's having the total weight of 3.1 ton currently, with payload and fuel weight. And it's going to be very much important aircraft strategically for the defense sector. So that I have done initial calculations of hybrid power source for this thing. The important challenge for this is energy density. Here, whatever the approach I consider that I'm going to explain now, the fuel capacity has been calculated, and based on the fuel capacity from the Austro engine performance currently, whatever the engine they are using, based on that fuel capacity is considered. And based on that fuel capacity, the energy input for the aircraft is calculated. Considering the thermal efficiency, currently they are using diesel engine, current thermal efficiency of the diesel will be 30%. So that whatever the energy input is there, that has been calculated. Here in this case, as we logically also go that the battery is having the important limitations in terms of weight, so that I consider the hybrid propulsion, that is solar plus battery electric configuration plus range extender I considered. Here in this case, the solar energy available for the fuselage and other area, that has been calculated, and solar power which is available throughout the cycle of this UAV. That is, UAV is having the endurance of 24 hours. There are about 12 hours of 12 hours of solar energy will be available. So that solar power available from the UAV point of view has been calculated. And whatever the other inefficiencies that are there in terms of power flow line, that has been considered. So here, this is a tentative calculations. I just want to convey that the power, if I'm using a range extender right from the 55 horsepower to the 240 horsepower, it's having the fulfillment in terms of 16% to the 73%. And if you consider the solar power, then it is fulfilling the need near about by only 1.86%, near about 2%. So that the other power requirement will be there, that has to be cut from the battery side. If you consider the currently even Tesla lithium ion specific weight of the battery, then there will be a huge battery capacity will be required. And for that thing, I calculated the weight. The weight will be very huge, near about the battery weight will be about 3,000 kg to the near about 10,000 kg. So that is not going to be very much feasible in terms of using the battery plus range extender in this capacity, because the aircraft weight itself is 3.1 ton, and we require a battery of 3.1 ton to the 10 ton to cater this electric requirement. So what will be the alternative is reduce the endurance of the hybrid electric UAV. That is, instead of 24 hours, we can calculated have done the iterations for the 12 hours and 8 hours. And right from 55 horsepower to the 280 horsepower I considered. And we can see that if we are reducing the endurance, then about 260 to 280 horsepower, there will be a weight penalty is less than near about 500 kg. So that in order to make feasible this hybrid propulsion at the current technological level, we need to go for a near about 260 to 280 horsepower of range extender and with reduced endurance. Here, the important point we need to consider is that the cycle effect I have not considered. Here, the cycle effect is not considered. The average power to the peak power. In case of automotive, that we calculated is about 30%, but average power to the peak power in case of a unmanned aerial vehicle or aerial application is going to be near about 70 to 80%, because in terms of UAVs, the vehicle will be running continuously between the average power to the max power, which is not the case with automotive. In automotive thing, we're generally running at the lower RPM only, but in case of aircrafts, we're running at only higher RPM only most of the time. So that that cycle effect I not consider, but if near about 25% cycle effect is considered, then this calculation can be refined. So what are the other options are available with us? That also I need to see that by means of apart from reducing endurance and increasing the range extender size, the wing loading methodology can be considered. This wing loading is nothing but a here the mass of the UAV and the area of the UAV is considered, and lift force and the wing loading, if you compare, we're getting a different parameters. And if you consider these different parameters, the wing loading for the amount of wing loading for the currently UAV applications can be calculated. Only this wing loading we need to keep it constant, and other parameters we can change. So that if we are reducing the mass, if the vehicle, the mass of the aircraft can be reduced to some extent, then this wing loading can be maintained, or by increasing the wing area, then by reducing the aircraft speed to some extent, just like in Tata Nexon, in conventional vehicle near about 150, 180 is the maximum speed, while in case of electric vehicle they have limited the speed to 120 kmph. Just like in the aircraft, if you are limiting the speed, then in that case we can go for a lesser wing loading, and by optimizing the wing profile also we need to see. Suppose the wing loading is, if you are considering near about 5% only, then in that case if you consider the same for the same wing loading, wing area can be increased by near about 5%, then the additional weight of near about 500 to 600 kg for the increased range extender size can be catered. So there are some experiment by the Siemens for series hybrid electric propulsion, and there are some Israeli Air Force applications are there for the hybrid electric propulsion. Such type of experiments are also going to be carried out, and it's having the same electric series range extender concept applicable just like electric vehicles. Yeah, then if you're going for a development of an alternator, the currently whatever the 23-27 kilowatt of alternator size we are told, that off-the-shelf alternators are also available from some of the off-the-shelf alternators are also available. If you're going for a indigenous development of the alternator, that also option can be opted. For that thing, as I told initially, that minimum BSFC RPM has to be tuned. As I told that 65 HP horsepower is the electronic fuel injection EFI engine, and this EFI engine maps and all that things are available with us. The engine mapping were carried out for the minimum BSFC RPM, and whatever the maximum power available at 6,500 and minimum fuel consumption with respect to many other various parameters, just like manifold absolute pressure, temperature, exhaust gases, that air fuel, considering the air fuel ratio or a lambda ratio, all the parameters we can consider, and we can find out a particular point where we are getting a maximum horsepower with a lesser fuel consumption. For that thing, the vibration analysis and all that things were carried out. This is the FFT analysis at the 4 channel. The engine has to be silent also, because if you are going for a lean mixture, because obviously for reducing the fuel consumption, you have to go for a lean mixture. There will be increase in temperature and there will be increase in roughness of the engine. So that the vibration analysis and all that things at the current rate we have calculated, the FFT analysis were calculated, and based on that, what are the engine mapping when we are carrying out, that engine mapping has to be checked, and the vibration and all that things has to be within that limit only. So currently this is the only the feasibility study. Preliminary study is carried out from the my organization point of view. Now the next step is to go for a practical experiments. Currently practical experiments, and to prove this concept. This is the initial feasible calculations, preliminary calculations that were carried out. And I just want to summarize our talk, that the electric vehicle is going to be very important, but because of its range anxiety and the charging infrastructure limitations, we have to go for a range extender. And this range extender is having it will reinstate the confidence on the electric vehicle, and it will reduce the cost of the electric vehicle first of all, and secondly the range anxiety can be eliminated till the charging infrastructure is available or some important breakthrough in the battery technology is happening. So this can be a feasible alternative for the automotive industry. And we already seen near about only the 25 to 40%, 25 to 30% we can say will be the size of the range extender, which will be a very small size. Even Tata and Mahindra, they are telling that it will be near about two-wheeler engine that can be fitted. It's not at the backside of the some of the vehicles, which will run the four-wheeler itself, so that the range extender will be on the lower side, and there will be a slight variation based on all the parameters, and for any particular vehicle that can be calculated. It's having the important advantage in terms of APU, also auxiliary power unit, and in terms of hybrid propulsion also, we can see that there is a feasibility by compromising some parameters in terms of endurance, wing loading by keeping the same wing loading, and other things. Then alternative selection, and I would like to convey that this is a similar concept, so that it is not only limited to the Wankel engine. Wankel engine is having the important advantage in terms of power to weight ratio and specific value. It can be applicable for any other range extender application, just like for the sake of fuel cell or micro turbines, or in case of a reciprocating engine, similar concept can be used and can be made it feasible. Yeah, that's all from my side, and thank you so much to all the audiences for listening me patiently. Thank you so much.
Yes, thank you, sir. Yes, sir.
Yeah, in case some questions and answers are there,
Yes.
I would like to take it, as the time is quite limited, but if there are questions are there, I would like to.
Yeah, first of all, thank you very much, sir, for sharing your research with us. Such a nice presentation is there. Thanks for sharing that research experience and knowledge with us. Now the forum is open for the all professor and research scholar. If you have any query, please ask. Hello.
Yeah.
Okay, sir. I think all the people are hungry now.
Okay, right. It's
Yes,
quite
sir.
late.
Because, yeah, it's 2 sessions already have done. Okay, sir. Thank you very much for the session and the nice presentation.
Thank you so much, sir.
Have a good day.
It's a nice interaction.
Thank you so much, sir.
Thank you, sir.
Okay, the participants can leave, and please meet at 2:15 p.m. with the lectures of an eminent professor from Jadavpur University, Kolkata. Many have maybe know about the Jadavpur University, which is a present and internationally recognized premier university of the country. The program are directed towards the achieving excellence in education and extending the benefits of improved technology to the society as a whole. So please attend the session on MR damper, which is a new, maybe you can say that suspension system, which is mostly now used in the Mercedes-Benz only. So that magnetological damper, MR damper. So please attend the session. Those are very interested in the automotive or the suspension system, shock absorber, vibrations related. Professor Gautam Puit is a professor at Jadavpur University. The senior professor is there. So please attend the session. Okay. Now I am leaving the meeting, and we'll meet at 2:15. Thank you very much. Please fill the attendance. I shared in the chat box. Morning sessions attendance I have shared in the chat box.
Okay, thank you, sir.
Yeah, thank you, sir.
Okay, thank you, sir.
Thank you.